And so we talked about deadlock prevention and deadlock avoidance. Now we said the second option is to allow the deadlock to happen and then have some strategy to detect it and as well as recover from it, right? So in the extreme, we can actually call the deadlock detection algorithm every time a request for an allocation cannot be immediately granted. So in this case, we're not only going to identify the set of threads that are deadlocks, but also we will know specifically which thread did cause this deadlock to happen. There's also a less alternative to this extreme use case, again, which is about frequency. When do we apply the detection algorithm? We can say, okay, we can call the algorithm at defined intervals, for instance, once per hour, or whenever we see that the CPU utilization that drops below a certain threshold, for instance, 50% or so. So to apply the safety detection algorithm, it's similar to the safety algorithm with the bankers. So here we're going to have a example again, and you can look at the pseudocode in the notes. So we assume that we have initially A, B, C resources, and this is the different threads that are and their corresponding allocation as well as the requests and the total available in the system, which is at this point 0, 0, 0, and we're trying to detect the state of the system. Okay, and so we're going to again set the done or the finished data structure to false for all the threads that are currently holding some resources, which means they're still in execution. And then we'll check their requests and see if we can find a safe sequence that will tell us that our system is in a safe state. So T0 is requesting 0, 0, 0. So we can start with T0 in our sequence, and we need to update the available to 0, 0, 0 plus what is currently held and allocated to T1, sorted to 0, which is 0, 1, 0, and this will equal to, let me erase this. So this will equal to 0, 1, 0. And then next, can we do T1? No, not yet. Can we do T2? Yes, we can. So don't forget to set this state, finish state to true. So we can do T2, and then we're going to end up with 0, 1, 0 plus what is currently held by T2, which is 3, 0, 3. And this is equal to 3, 1, 3. And then we set the state to true. Can we do T3? Yes, we can. And so it's 3, 1, 3 plus 2, 1, 1. And this is equal to 5, 2, 4. And we set T3 state to true. Can we do T4? Yes. And this will give us a total of 5, 2, 4 plus 0, 0, 2, which is 5, 2, 6, and T4 is set to true. We go back to the remaining one, which is T1, and finally it's 5, 2, 6 plus the current allocation to T1, which is 2, 0, 0. This is equal to 7 instances of A, 2 instances of B, and 6 instances to C, as you can see, which is what we have in the system. And then we set T1 to true. So we forgot to do the, don't forget to save the order of execution. So we did T0 first, and then we did T2, then T3, then T4, then T1. So this is our save sequence, and we check the done or finished states of all of the threads, and we see that all of them are true. Therefore, we detect that our system is in a safe state. Okay, so now if we assume the same system, but the difference is that T2 will request one additional instance of C. So originally it was 0, 0, 0, but now we'll change it to 0, 0, 1. And let's apply the safety algorithm and see what's the current state of our system. Again, the current available is 0, 0, 0. So gonna set the finish or the done state to false for all of the threads or processes. And then can we service T0? Yes, the request is less than available, and we're going to end up with 0, 0, 0 plus 0, 1, 0, and this is equal to 0, 1, 0, and process T0 is finished. Can we service T1? Not yet. Can we service T2? Not yet, because we don't have this one instance of C just yet available. Can we service T3? So our current save system has just T0, right? Save sequence. Okay, so let's continue. Can we service T3? No, we cannot. Can we service T4? No, we cannot. And therefore we're done, right? And then we're gonna check the done or finished state of these threads, and we're gonna see that we do have only one thread that can safely finish. However, the rest will be in a deadlock situation, and we're gonna end up with an unsafe state. Now that we've learned about how to detect a deadlock, now how can we recover from a deadlock situation? So there are two options. The first one is to simply abort one or more of the threads to break that circular wait. Now, the problem is that the deadlocked processes may have already computed for a long time, and the result of these partial computation must be discarded and thrown away, and probably will have to recompute again later. So if the partial termination method is used, then we must have to choose a victim, right? We must have choose which deadlock process should be terminated first. And there may be a lot of factors to take such decision. For instance, the priority of the threads and how long the threads have been computed so far, and so on. So there's a lot of considerations to think about if we choose this option to recover from the deadlock. The second option is to preempt some resources from one or more of the deadlocked threads. So the idea is we successively preempt some resources from those threads, and we give them to the other processes until the deadlock cycle is broken. Again, how can we select a victim? So maybe we say, okay, we're going to select a victim depending on the number of resources that a deadlock process is holding, or again, the amount of time that it has been running thus far. And another question is what we do with that victim once we take away the resources that it has been holding. Then what should we do? One idea is a total rollback. So we completely abort that thread or that process, and then we restart it back again. Another dilemma or another concern here is what we have to somehow make sure that a process is not picked as the victim every time. So we have to somehow ensure a policy that one process can only be picked as a victim just once, or only a small finite number of times to again avoid the starvation of the process. So you can see that there's multiple considerations and there's a lot of overhead and a lot of headache that comes with enforcing strategies to detect, avoid, to prevent, avoid, detect, and recover. And you can see now why some operating systems choose to just look away and ignore completely this problem, and think that the developers will be responsible enough and aware enough that they won't create software that causes deadlocks because there's so much overhead to handle it.